Hi, my name is Pranav Sridhar, and in today's lab, I'll be analyzing the motion of a tennis ball rolling on a smooth surface with the help of Newton's second law of motion. Knowing this, we will be able to predict the ball's position at any given time. Given that we were asked to observe the motion of an object moving at constant velocity, we will assume that the velocity does not change, which implies that both the acceleration and net force are zero. This statement is in fact Newton's first law of motion, which states that an object will remain in rest or in uniform motion unless acted upon an external force. The lab, if done correctly, should prove Newton's laws of motion, which, as we all know, is crucial in the way we understand motion and the groundwork for a lot of the physics that we know now. Here's a video of a tennis ball rolling in the positive x direction on tracker. Right off the bat, you see the tennis ball on the table with the axis on it. To answer the what if question, I decided to place the origin at the center of the ball, as seen on the video. Because when analyzing the motion of an object that's relatively large, we use the center as a point of reference. If I had reversed the axis, I would have gotten negative x value, which wouldn't make as much sense given that the ball is moving in the positive x direction. Moreover, I used a ruler to measure the actual diameter of the tennis ball and confirm the length online. And then with the help of the calibration stick, I was able to calibrate it properly in order to get accurate data. I also kept a notebook on the table to make sure the ball doesn't deviate from its horizontal path. As the ball rolls, you see the point masses that I've added. I did my best to place the point masses at the center of the ball because, as I mentioned before, that's our point of reference. At first glance, the velocity does indeed seem constant. However, when you look closely at the point masses towards the end, you see that they're more clumped up than the other points, and this is also reflected on the graph to the right. That means the ball does slow down ever so slightly, which would suggest a change in velocity and a non-zero net force caused by a force that hasn't been accounted for in our assumption that the ball is rolling in constant velocity. To answer the what does it mean question, knowing exactly what forces act on the object and cause this change in velocity is almost impossible. But based on my knowledge, I've come up with a pretty good guess. This unaccounted force will be discussed later in the lab. Now that we have our observed data, I went ahead to code a predicted model of the motion of my tennis ball. Note that this predicted model assumes that the ball travels in a constant velocity. As you can see in this snippet of my code, which I used to set my initial conditions, I unfortunately did not have a balance. Therefore, I looked up the mass of a standard tennis ball. However, it's important to note that the mass does not matter for this predicted model, as I'll explain shortly. The x component of the position vector has been taken from tracker. Given that we are only analyzing the motion in the x direction, we left the y and z components as zero. The ball velocity was calculated by taking the initial point and the point right before the line begins to curve. The initial time has been set to zero and the delta t has been set to 1/60 since I filmed my video on 60 frames per second. What this allows me to do is to get the same number of data points as I got in my observed model in Tracker, which will make it easy to compare as we'll see shortly. Further down my calculation loop, you can see the two important formulas that are derived from Newton's second law of motion. Going back to why mass doesn't matter for this model goes back to Newton's second law of motion. Since the force vector is a zero vector in this case, you see that the mass has no effect on the ball's velocity since 0 divided by anything is 0. Here's a graph that compares the observed and the predicted model of the tennis ball's translational motion. As you can see, the two lines almost overlap each other until the very end when the observed model begins to curve. In the beginning, I briefly mentioned the possibility of an unaccounted force, so I'll go a bit in detail. In this free body diagram we saw before, we assumed that there are only two forces, weight and the normal force, which thereby balance each other out to give a resultant force of zero. However, now you see the potential unaccounted force that I mentioned. That force is a force of friction. Given that there's nothing countering this force of friction in the x direction, there's a non-zero net force And according to Newton's second law of motion, we know that there is a non-zero acceleration, which means velocity is not constant as assumed. Though the objective of the lab was to analyze the motion of an object moving constant velocity, this simple motion allowed us to explore a lot more than that. Thank you for listening.